topic to me as a serious allergy sufferer, and then other atmospheric processes. First, I'd like to invite Mr. Hlakosta to come and talk to us about the meteorological drivers that influence how dust is transported from the Namib desert towards the southern part of Angola.
Thank you. Greetings to you all. My name is Hlakosta Hlakosta, so I'll be presenting the first objective of my research study, which is meteorological drivers of the dust emission potential from southwestern Angola. So I'll be focusing on the machine learning. Okay, so wind-blown dust with dust particles less than 100 micrometers is a major source of nutrients to terrestrial and oceanic ecosystem. So it originates from natural sources such as deserts, dry lake beds, and from anthropogenic sources such as unpaved roads, mining and quarrying, and agricultural farmlands. So the significant global sources that are highly known include the Saharan Desert, found in North Africa, the Patagonian Desert, found in Argentina, the Tigris-Euphrates Basin, found in the Middle East, the Aire Basin, found in Australia, and the Owens Lake, found in the United States of America. So the key sources we have in Southern Africa include the Makgadikgadi Pen, found in Botswana, the Etosha Pen, found in Namibia, the Southern Kalahari region, the Namib Deserts, and the Free State Pens. So the problem under investigation is that the southwestern Angolan region is associated with arid and semi-arid climates, which makes it highly prone to dust emissions. So it forms part of the Namib Desert that is highly known for its dust emission. Also, it features geographic features such as dunes, rough terrain, and less vegetation. So previous studies have identified that the Makgadikgadi and Etosha were the significant source in Southern Africa. However, later research using MODIS data highlighted that the Namib Desert was the major source. This was supported by the studies by Vickery et al. Vickery et al. 2013 and von Holt et al. 2017, whereby they identified that the Namibian riverbeds, pens, and wet areas accounted for about 34% in the Namib Desert, whereas Etosha and Makgadikgadi Pen accounted for about 11% and 16% respectively. So there is limited characterization of dust in Angola, despite it being part of the Namib Desert that is known for its frequent emission of dust. So this is because dust is not frequently emitted from Angola as compared to Namibia. So particularly a short study by Bilele et al. That of over 2 years identified that the primary dust drivers in southwestern Angola were the Benguela level jet and the Angolan jet. So my study will build up on their study, whereby I will identify meteorological drivers of dust using machine learning with a period from 1995 to 2019. So this is the study area map of my focus area, which is southwestern Angola. So this is the outline of my data and methods. So I'll start explaining what is self-organized maps, why am I using self-organized maps, and the methodology around self-organized maps. And lastly, I will try to validate my ERA 5 data using 15 in-situ stations from the SASCAL network. So the self-organized map is an unsupervised classification technique that clusters similar data together to make it easier to understand high-dimensional data such as ERA 5 data that I'll be focusing on. So this similarity is seen by similar maps or nodes that are closer to each other. So self-organized maps, they do not require labeled data. Instead, they self-organize to identify patterns and structures within the input data. So we use the self-organized map technique for atmospheric circulation patterns classification over southwestern Angola to study synoptic circulation patterns occurrence linked to dust emissions. So we tested the self-organized map classification using the Minnesota Python library on the Jupyter Lab. And then we chose 12 nodes for our study. So the training period, as I previously explained, was from 1995 to 2019, which is about 9,131 days, because it's very important on our self-organized maps, the days. And then the data, we collected the data from ECMWF, which is ERA 5 data. And then the meteorological variables we focused on was included precipitation, wind speed and direction, mean sea level pressure, temperature and relative humidity. So for the sake of time, I will focus on the seasonality, not, yes, I'll just only focus on the seasonal part of it. And then the geographic region we focused on was southwestern Angola, as we explained. So this is my methods for ERA 5 data validation. So we validated our ERA 5 using 15 in situ automatic weather station from the SASCAL network. If there are data ranging from 2014 to 2019, and we collected daily values for each month in all the years. So when we analyzed our data, we replaced missing values with null values. We replaced data gaps with null values, and then we chose 95th percentile to ensure data validity. And then the variables that we focused on include rainfall, temperature, wind, relative humidity, and sea level pressure. And then the statistical metrics that we used include regression slope, coefficient of determination, and root mean square error. So this is our result for our machine learning. And this is mean sea level pressure. So in summer, the Angolan low were found on the interior of the southwestern Angola, bringing higher rainfall in the interior. So these conditions are not suitable for dust emission due to increased moisture. So during winter, there is a persistent influence of South Atlantic high from the west coast, and Botswana high sort of like comes up towards the interior of the southwestern Angola. So these conditions are associated with stable, dry conditions that make winter the highest potential for dust emission. So autumn and spring show similar conditions to both winter and summer. So I'll try to focus more on winter and summer on this presentation. So this is this is the self-organized map for precipitation. And the key factor here is that low precipitation that is less than 2 millimeters per day increase high dust emission. So from the study I've read, low precipitation that is below 2 millimeters per day dries out faster, normally within an hour. So the one that is greater than 2 millimeters per day sort of like takes weeks or months to dry out. So our key factor here is that low precipitation that is lower than 2 millimeters per day increase high dust emission potential. So during summer, even though summer is a rainy season, most days fall below 2 millimeters per day within our study area. So making dust highly possible to occur. So during winter shows dry conditions, which also it falls below, rainfall it falls below 2 millimeters per day, making dust highly possible to occur. So autumn and spring shows similar conditions to both winter and summer. So this is the case in all my meteorological variables. So this is a self-organized map for wind speed and direction. So the key factor here is that wind speed greater than 2 meters per second is the primary driver of dust emission potential. So I followed the study by Cowie et al., whereby they identified that wind speed that is between 2 and 5 meters per second sort of like increase high dust emission potential. So during summer, from our analysis, summer reflects strong onshore winds from the South Atlantic High and Benguela Current. Winter, we can see by the persistence of southerly winds influenced by the South Atlantic High pressure. So spring and autumn shows similar conditions to summer and winter. So, and then this is a self-organized map of relative humidity. So the key factor here is that lower relative humidity that is lower than 50% reduces soil particle cohesion, making dust more vulnerable to wind erosion, making it highly possible to occur. So in summer, there's high relative humidity that ranges between 72 to 90%. So higher relative humidity adds surface moisture, making dust less likely to occur. So during winter, winter is associated with low relative humidity that is between 32 to 64%, making dust highly possible to occur. So also from the studies we've read is because the relative humidity that occurs is because the Benguela Current's cooling effect generates low stratus clouds and fog over most of the winter. So this is my self-organized map for temperature. So temperature, high temperature and low temperature still contribute to high dust emissions. So in summer, it's associated with high temperature values that ranges between 22 to 25 degrees Celsius. And winter is associated with low temperature values that is between 12 to 22 degrees Celsius. So from the studies I've read, they said that higher temperature lead to an increase in dust emissions, and lower temperature also lead to an increase in dust emissions due to frozen winds and winter conditions in general. And then these are my results for ERA 5 data validation. And then from my results, we've identified that temperature, mean sea level pressure, and humidity showed the strongest agreement. And then the weakest agreement was found in wind speed and precipitation. So this aligns with the study from Europe, whereby they also identified that ERA 5 data doesn't perform well when it comes to wind speed and precipitation, but it performs well when it comes to temperature, mean sea level pressure, and relative humidity. So in conclusion, from our analysis, dust occurs across all seasons, with winter being the most dominant. And then the Sascal weather station should be well maintained for data accuracy and outputs, since there is low data collection there. And ERA 5 performs well in the southwestern Angolan region, but caution needs to be taken when it comes to wind speed and precipitation. And I would like to thank Dr. von Holt for the development of machine learning method. And then I would like to thank my sponsors, which is NW, Mine Dust Network, and National Research Foundation. Thank you.
Thank you, Noel. Very interesting stuff and some beautiful pictures you have there. I'd like to invite our next speaker. It's Dr. Let me just get it right, Mkololo. She's from the South African Weather Service, and she will share with us a statistical analysis of 20 years of ozone data that's been measured at the Cape Point monitoring station, and compare that to some satellite data, which will be very interesting. Thank you. It's the green button. That one. Okay, the big one.
Good afternoon to everyone. It is good to be in my home province. I was so excited when I get to Eastern Cape. So I was so excited when I get to Eastern Cape. So I'm Tumeka Mkololo, working at South African Weather Service. So we are based at Cape Point Global Atmospheric Watch Station. So I will present the 20-year statistical comparison between the Cape Point surface ozone data and the satellite observations. So I'll just follow that outline, which has the NACA structure, which is the introduction, the method, the results, and the conclusion. Okay, so at firstly, let me take you to Cape Point Station without wasting any time. So the Cape Point Global Atmospheric Station became operational in 1978. So as you can see that red circle there, it is where the Cape Point Station is located. So it is located there, and we are performing some of the measurements like the greenhouse gases and the trace gases. We also have the regional GO stations that we have in the country where we monitor the UVB, and also we do the total column ozone observations at Irene, Springbok, and in Cape Town. However, for this presentation, I will just focus on the surface ozone measurements. So the Cape Point Global Atmospheric Watch Station is one of the 33 World Meteorological Organization GO stations that monitor the ambient surface ozone concentrations at background levels. So we started monitoring surface ozone in 1983. So this study was just basically, we compare the surface ozone data from Cape Point with ARS satellite together with the MIRA-2 reanalysis data. So I've chosen these two satellites because the data is easily accessible. And for this study, I've used the data from 2003 to 2024. So the Cape Point Station uses the thermoscientific instruments for continuous monitoring of surface ozone. So we normally do our quarterly verifications using the primary calibrator, which is traceable to EMPA. So all GO stations are audited every 4 to 5 years. So over the past years, Cape Point Station have been performing well during the audit, with the exception of the 2021 audit where our calibrator was having some problems. However, we have corrected the data after the audit and submitted the data to the NELU database. So that one is just to show you our history of the audit that we had from Cape Point, starting from 1997, as you can see them. So the recent audit that we have was in this year during March. So moving to the ARS satellite, so it was launched in May 2002. It is one of the instruments on board of NASA Aqua satellite. So ARS measures the atmospheric composition, air quality, humidity, and other parameters as well. So the data is available on daily, for daily and monthly daytime and nighttime. Starting from 1,000 hectopascals to 1 hectopascal pressure levels. So for this study, I've acquired the data from Giovanni. Moving to MIRA-2 reanalysis data. So MIRA-2 is the reanalysis of version 2. MIRA-2 is the version 2 of MIRA. So it was launched in 2002 to improve MIRA assimilation. So I've used the spatial resolution of 0.5 to 0 times 0.625 degrees for 3-hour resolution. So MIRA-2 was introduced to continue the global modeling and assimilation office obligation of continuous climate analysis. So similar with the ARS, we have acquired the data from Giovanni. Okay, so let's see what is happening there with the results. So the histogram graphs indicate the distribution of ground-based measurements and the satellite measurements. The first one will start by looking at the thermo, which is the instrument that is based at Cape Point, so followed by the ARS satellite and MIRA-2 reanalysis data. So as you can see from the columns there, so the observations, we had 263 data points. There was no missing data. Then looking at the minimums there, so you can easily see that the ground-based measurements, we had a minimum of 14.8, for example. When you look at the satellites, you see that now you start to see higher concentrations. So for example, for the Mira-2, the minimum was 39.8. So looking at the maximum, for example, you have Mira-2, which had recorded a maximum of 64.67 during the study during the study period. Then the mean was 47.39, for example, for the Mira-2, whereas the ground-based observation mean during the study period was 25.4. So you can basically see from the results that the satellites slightly overestimated the surface ozone concentrations at Cape Point. So it is not that bad, because even though the satellites that I've used in this study overestimated the surface ozone concentrations, but then when we're looking at the seasonal pattern, they follow the same seasonality. So at least there's something positive that we can get from the satellites as well. So if you want to check at the seasonal variations, then you can also consider the data from satellites as well. So we also conducted the trend analysis. So we used the main candle to calculate the candle's towers, the sun slope, and the significance of trends during the study period. So the sun slope, so it is the average of all the slopes calculated between each pair points in the series. Then the candle's tau measures the monotony of the slope, so it varies between -1 and 1. So it is positive when the trend increases, and it is negative when the trend decreases. So in order to get whether the trend is significant or insignificant, we consider the p-value. So if the p-value is less than 0.05, then that trend is significant. So if it's higher than that, the trend is insignificant. So looking at the ground-based measurements, which is the first row thermo, so we see that there is a trend, so p-value was 0.002. Whereas looking at the ARS, the p-value was greater than 0.05. So whatever we see there, the trend, there's no trend because the p-value was above 0.005. Similar thing happened with the Mira-2 observations as well. Okay, so that there I've calculated the performance, the percentage difference between the ARS and the ground-based observations, and also did the similar thing with the Mira-2 and the ground-based observations. So my apologies, I've noted that I've used an incorrect unit at the end there, so it was meant to be a percentage, not a ppb. So we can see from the graph there, which has A, for example, the percentage difference between thermo and the ARS, you see that the data varies between 5% and -16. So the average of that variation is -5.6. Then looking at the B graph, which is the percentage difference between the thermo and the Mira-2. So the percentage difference varied between 5% and -26%. So which means that the Mira-2 overestimated the ground-based measurements by 5.47%. So I started by doing this case study, for example, a few years ago. So that was the motivation behind to use the surface ozone data as well to check the differences between the ground-based and the satellites. So previously I used the same satellites, which is ARS and Mira-2, but then in this case I was calculating the percentage difference for the total column ozone, which is basically the stratospheric ozone. So as we can see from those graphs there, you can easily see that the percentage difference was a bit lower than what I previously presented for the surface ozone, for example. So this one, for example, the first one, which is the Mira-2 and the Dobson, so the percentage difference was only 2.17%. So which means there is almost a good agreement if we consider the satellites in the for stratospheric ozone measurements than the tropospheric ozone measurements. So similar thing happened with the ARS and the other satellites that I used, the OMITOMs and the OMIDOS. So the difference was within 4%, unlike what I previously presented of high difference of 15 point something percent, which was higher. So the satellites performs better in the stratosphere when it comes to ozone observations. So if you are interested to access our data, so we submit our data annually to NILU database, so you will find it there. So it is in 1 hour resolution, so our data is there from 1983 until 2024. So in conclusion, I would like to say the ARS and MIRA-2 struggle to quantify the actual surface ozone concentrations at K point during the study period. So the ARS and MIRA-2 seasonal patterns agree with the thermo-seasonal cycles, as I've already indicated them. So the MIRA-2 and the ARS overestimated the surface ozone. So based on these studies that I've just shared, I can say that the K point data, based on the studies at K point surface ozone and the Stellenbosch total column ozone observations, the ARS and the MIRA-2 compare better with ground observations, which we consider the stratospheric observations. So in this case, we use the Dobson's instrument for the stratospheric observations as compared with the surface ozone measurements. Thank you, Enkos.
Thank you, Dr. Mkololo. Our last speaker is Ms. Podile from the Northwest University, and she will talk to us about the influence of meteorological parameters on pollen concentrations, but specifically in Sharpeville and over 2 seasons. Thank you.
Good afternoon, ladies and gentlemen. As introduced, I am Genelo Podile from the Northwest University. I will be presenting partial results from my master's study looking at the influence of meteorological parameters on pollen concentrations in Sharpeville. I will focus specifically on 2 seasons, looking at 2 months. So about 20 to 30% of South Africans suffer from pollen allergies. But first, let's define what pollen is. Pollen is a fine, powdery dust that is produced by plants when they reproduce. But not all the pollen that is released from these plants is allergenic. Pollen that is mostly allergenic is from grasses and from ornamental exotic trees, which are usually planted in cities and towns along alleys and roads, such as your plane trees, oak, and birch. So when you have a sensitized individual who gets exposed to these allergenic pollen grains, they get allergenic symptoms. So when you have increased pollen concentrations in the atmosphere, the symptoms of the sensitized individual gets worse. So there's evidence that shows that pollutants amplify the pollen-related allergies, which makes it interesting to do aerobiology studies in urban areas. However, most of the aerobiology studies that have been done are concentrated in the Northern Hemisphere, despite the fact that the sub-Saharan Africa is a rapidly industrializing region. There has been, looking at the Vaal Triangle area, there has been a study that was done between 1991 and 1992 as part of the VAP study by the SAMRC, which did consider the allergenic pollen. But with land use changes, the pollen allergy profiles will change, and so this data needs to be updated. There is also progress in terms of aerobiology studies in South Africa with the formation of the SWNet, which is the South African Pollen Monitoring Network, which has 9 sites across 6 provinces since 2019. The 9 subnet stations are placed across different biomes within these 6 provinces. And this is because with distinct climate regions that have diverse vegetation differences, you will have varying pollen allergy patterns. So it is important that we have site-specific aerobiological studies conducted. And since climatic regions are a factor, it is important to therefore look at the meteorological influence, to look at the pollen dispersal, the atmospheric transport, diffusion, and therefore deposition of the pollen grains. Understanding the relationships between meteorology and pollen concentrations will help us understand the allergen exposure risks for sensitized individuals. So the aim of the study is to compare how the weather conditions affect the concentrations, and I said I will compare 2 months because it's 2 distinct different seasons, but I only focus on October, which is late spring, and February, late summer. Oh, okay, I thought it was missing. So how we collect the pollen data, first, for my master study, I monitored from June 2024 to June 2025. So how we collect the pollen data is we use a volumetric spore trap. So for this study, we placed the spore trap on top of a SOARS weather station in Sharpeville, and it was at a 2.5 meter height, which is around the level at which sensitized individuals live and breathe. So this instrument draws in air at 10 liters per minute, and the airborne particles, which include dust, pollen, and fungal spores, are impacted onto a Melanix tape. This Melanix tape has to be changed every 7 days, and in our case, it's on Mondays. And then we cut the Melanix tape into 7 pieces for representing the 7 days. We mount them on microscope slides using glycerin jelly, and we identify the pollen using optical microscopy. To see the different pollen, we use pollen morphology, and I'll show you in the pictures as I continue. And I count at 400 magnification, and it is according to the subnet standards. The concentration of the pollen is in pollen grains per cubic meter. And then for the MET data, for the meteorological data, I got the data from SAQUIS, and I looked at temperature, wind speed, relative humidity, and rain. I did not look at wind direction in this study. Some data was missing in February, so I used simple linear regression to fill in the gaps using a nearby site, the Northeast University Val campus station, which is less than 5 kilometers away from the site. Then for statistical analysis, I used daily mean averages for all my parameters, and I performed the Spearman's correlation test, which looks at the nonlinear relationships between the parameters and look at the statistical significance. So these are the first results. So in both months, we got a total of 35 different pollen types. But we only look at pollen types with the pollen with a percentage composition of over 1%. So I spoke about morphology earlier on, and these pictures show that pollen does not look the same. It has different sizes, different shapes, even different textures that can affect pollen dispersion. So first we'll look at October, which is late spring. So this month was dominated by tree pollen, which is expected as it is spring. Trees tend to flower. Trees tend to require lower temperatures to flower when compared to your grasses and weeds, and so we see lower concentrations for that in contrast to summer, where now we have a lot of grasses and lower tree concentrations. The only tree that was identified in February was elm tree, and we also have our weeds, Cyperaceae and Plantagenaceae. And then when we look at the weather conditions for both months, in October, the temperature fluctuates more when compared to February, and this is true for your wind speeds and your humidity. So in February, we have more stable weather patterns, which allow us to actually see the relationships between the meteorological parameters, as the next slides will show. So now we'll look at the Spearman's test results for October. the p-values that show the statistical significance is a p-value that is less than or equals to 0.05, which is shown in blue, and 0.01 shown in gray. So the gray ones are statistically highly significant. First, we'll look at Fraxinus, which had R value of minus 0.57, and it's a positive relationship, meaning as temperature increases, Fraxinus concentrations also increase. So the Fraxinus counts in the month of October did actually coincide with lower temperatures, which proves that trees require cooler temperatures to flower. Myrtaceae from the eucalypt tree is insect pollinated, but it has a positive relationship with relative humidity, which shows that dry conditions are required for anther dehiscence, which is when the pollen is actually released from the anther. And then next we have Ericaceae, which is the palm tree, Casuarina, which is the Australian pine tree. Their peaks coincided with higher wind speeds, which show that wind speed is important for pollen release. Now let's go to February, where we have more consistent weather conditions. So this allowed us to have to see clearer patterns for the relationships. So with temperature, all the relationships are statistically significant, and showing that warmer temperatures result in higher grass and weed pollen concentrations. Then looking at relative humidity and rain, when you deal with pollen grains such as your grasses and your weeds, they are quite big compared to tree pollen. So when they absorb moisture, they become heavier and they settle on the ground. I lost my signal. Okay, there. And then for wind speed, we have a mix. For wind speed, we have a mix of the relationships. For Plantagenesis, the relationship is positive, and then for the others, it's negative. So for grasses, you need slower wind speeds, as higher wind speeds can dilute pollen grains. So this shows that there might be some complexities in terms of pollen dispersal when looking at wind speed, as the relationships are not the same. To conclude, we've seen that February has a consistent weather pattern, which allowed us to see more uniform correlations between our different pollen taxa, whilst October had more varied individual responses. And then the complex relationships are with the wind, because wind actually aids the transport of this pollen, but if the wind speed is too high, it can dilute the concentration. So further studies need to be done to further understand pollen dispersal. This could be achieved by having a longer data set. It will also help us understand the seasonal variation, and look at the pollen seasons for the different pollen taxa. And this, understanding the relationships between meteorology and pollen will help us provide evidence-based data for clinical and environmental health applications. I'd like to acknowledge the GCC and the SAMRC for funding my project, ESCOM and the Northwestern University USEM, Dr. Brigitte, for funding us to come here, and I'd like to thank NACA for allowing me to present my work. Thank you.
Thank you very much. We've got 10 minutes for some questions. While you think of your questions, I have a few, and this is just my curiosity. How does a pollen trap work? How do you not catch other dust particles and just the pollen? Oh, of course, sorry.
So we do catch other particles. I don't know if you saw in the picture that I showed of the different slides. Some of the parts are black. That is the dust particles and smoke particles. So we do get dust particles. Sometimes the dust particles actually make it hard for us to see some of the pollen because it covers the pollen, and we usually have to just say, put an asterisk and say we couldn't identify the pollen because the particle loading was too high on those days.
But then it seemed like the pollen particles are quite a bit bigger than the dust particles, or do you find them
No, they are bigger.
by
They
much
are
bigger?
bigger,
So they're easier to identify.
identify, definitely, yeah.
Anything from the floor?
Thank you for wonderful presentations. Napo from Mintech. My question is to Dr. Mkololo. In 2018, if I remember correctly, there was a global scale adjustment of ozone measurement emanated from the, I think, significant study that was done between NIST, NOAA, and the BIPM on the, I think, measurements over sort of like, I think, 5 decades that resulted in the consensus of small adjustment of, I think, ozone measurements. I think that were also, I think, affected by the development of the standard reference photometer for ozone calibration measurements. Did that have a significant difference on the data from Cape Point?
I'm going to take the next question and then we can respond. Did you have a question, Warren?
Yes. Also for Dr. Mkololo. Well, actually, firstly, I want to commend everybody up there for sharing their work. I think you guys are doing a great job by just sharing your work, so well done. So, Tumeka, I'm curious about the satellites and the mismatch between what you see on ground level measurements relative to satellites versus Dobson column measurements relative to satellites. And I'm wondering if the satellites, are any ground-based measurements actually used to, calibrate the algorithm or to verify the satellite algorithm that basically gives you the satellite data? Or is it actually just tuned for Dobson-related data? That's the one thing. And then the second thing I was curious about is, have you ever thought of expanding that measurement comparison beyond just Cape Point, like comparing it with one of the reference stations at, as part of SAKI's or something, just to get an idea? Thanks.
Can you respond?
Thank you, Dr. Napo, for the question. So, with the adjustment of scales, so we only implemented the scale this year after the audit that we had in March 2025. So after the audit, then we were informed that all the GO stations now have to adjust to the new scale. So yes, we have to multiply our data by a factor of 1.1 or something. But then yes, it does increase a little bit. It had an effect on the data that we have. So from now onwards, we are using the new scale. So coming to Dr. Warren, so you are interested when it comes with the Dobson observations compared with the surface ozone observations. So most of the studies have been focusing on the stratospheric ozone observations, for example. As you can know that the stratospheric ozone has received a lot of attention within the scientific community. So most of the studies have been focusing on the stratospheric ozone because that's where most of the ozone is located. Approximately 90% of ozone is in the stratosphere, and only 10% is located in the troposphere. So it's not a lot of work that has been done when it comes to the satellites focusing on the surface ozone observations. So another thing that I think that we see this is the reason for this drift that we are seeing regarding the percentage differences when considering the stratospheric and the ozone, and the surface ozone observations. I've seen some studies that say that the lower stratospheric ozone has a faint signal. Remember, the satellites are not closer to the surface level. They are up there. That's why they are almost accurate when it comes to the stratospheric observations than the tropospheric observations. There is also a possibility that there is also an interference of some aerosols or clouds, for example, or also there is an interference of the stratospheric ozone. As you know, that most of the ozone is in the stratosphere. Maybe that's the reason that we see that high difference. Maybe some of that ozone that we see is the stratospheric ozone, is not even the surface ozone. That's why we see a jump of a mean. For example, when it comes to MIRA-2, you will end up having a 60-something mean compared with ground observations of 25 ppbs. So regarding the expanding of the study, I was thinking of expanding it as well and look at the other stations within the SAQUIS database. So I've tried previously to get some data from SAQUIS, but then I didn't manage to get it. So I will try again my luck. Maybe I'll be successful this time. Thank you.
Anyone else like to ask a question? Do you have a follow-up question? A different question? Go ahead.
Kenilwe, the identification of the pollen, you physically have to sit behind a microscope. Wow. So every week you get a weekly sample from Sharpeville, and then you sort of...
Yeah, it takes hours, and yeah, you just have to sit there and count. Some days have higher concentrations. You can find just pollen grains alone, the pollen concentrations being in the 300s, even the 400s, because at 2.5 meter, you actually find a higher concentration when compared to the standard subnet at above 10 meters height. So it means the people at closer to ground level are actually exposed to more pollen than we actually think based on the subnet data. So yeah, it was more work.
And then related to that, is there potential for automating that through, say, taking images of what the pollen looks like, developing some sort of library where you can see the images and then put AI on it to see, that's pollen, that's... are people thinking of that?
Yeah, some people have actually thought of that. There are studies that are done in China that use machine learning processes, taking pictures to help identify the pollen, and there's now also an introduction of automated pollen sensors. If there's someone from SOURCE here, I think they might have a bit more information on that, which basically uses AI and then pictures in the library to help identify that. But I think we still have a long way to go with the validation process and still teaching it to identify the different pollen types.
Thank you, everyone. Anyone else? A final round of applause for our speakers. Thank you very much for a very interesting session. I'd like to invite the chair of the next session. It is, let me just see here, Dr. Opio from Northwest University for our 3-minute sessions. Have fun.